Every time you flip a switch, you are witnessing one of the most successful manufacturing feats in modern history. We often dismiss LEDs as cheap plastic bulbs that simply replaced old glass filaments. But this narrative ignores the brutal material science required to make them possible for decades before they ever hit store shelves. The story isn't about marketing. It is about a physical battle fought at the atomic level on silicon wafers, where yield rates and thermal management determined whether light would remain an expensive novelty or become the universal standard we rely on today. The common assumption that LEDs are just better bulbs misses the profound engineering gap between incandescent filaments and solid-state semiconductors. For a long time, creating blue light was considered impossible for mass production because of a fundamental materials mismatch. The breakthrough relied not on inventing new physics, but on solving an immense manufacturing problem, growing high-quality gallium nitride crystals directly onto silicon substrates instead of the traditional sapphire wafers used in early prototypes. This transition from sapphire to silicon was the critical enabler that finally achieved cost parity with incandescent lighting. The reason this took so long is not a lack of clever ideas, but the sheer difficulty of bonding two materials that expand at different rates when heated without creating microscopic cracks throughout the entire wafer. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. For years, engineers tried to grow gallium nitride on sapphire because it was chemically stable, but sapphire wafers are small and expensive, limiting production volume and keeping costs sky high. The real game changer came from a manufacturing strategy that embraced silicon as the foundation for light-emitting layers. By successfully transitioning to silicon substrates, manufacturers eliminated the need for thick, costly buffer layers designed to manage lattice mismatch between the materials. This shift allowed factories to scale wafer diameters up to 8 inches, matching the infrastructure already used for computer chips. Suddenly, you could produce vastly more LED dyes on a single piece of raw material than was ever possible with sapphire, driving down the per-unit cost through sheer volume and efficiency in the fabrication process itself. However, simply growing the crystals is only half the battle. Making them survive assembly without breaking is where the cheap plastic myth falls apart completely. The early generation of LEDs relied on fragile wire bonds to connect the tiny semiconductor dies to their heat sinks. These thin gold wires were prone to failure under thermal cycling and added significant labor time during automated assembly, keeping final product prices high. Manufacturing engineering solved this by mastering a specific process known as flip chip bonding. This technique inverted the die so that its electrical contacts faced downward, allowing for direct connection through large thermal vias rather than fragile filaments. This shift in assembly methodology drastically reduced both material usage and machine cycle times. The elimination of wire bonds meant that heat could be dissipated much more effectively from the junction directly into the substrate, improving reliability and extending product life while simultaneously cutting out a complex manual step in the production line. The result was a component that was not only cheaper to build, but also mechanically superior to its predecessors. This engineering leap transformed LEDs from fragile laboratory curiosities into rugged industrial components capable of withstanding the rigors of mass-market consumer goods. The economic tipping point for this entire industry arrived when process optimization in metal-organic chemical vapor deposition, or MOCVD, reached a new plateau of precision. For decades, growing defect-free layers on silicon was difficult because thermal stress would cause dislocations that ruined the light-emitting regions. The breakthrough occurred when manufacturers pushed yield rates for these defect-free gallium nitride on silicon layers past the 95% threshold. Crossing this specific statistical barrier meant that the wasted material in production dropped to negligible levels, allowing the cost per photon of emitted light to finally dip below the price point of an incandescent bulb despite the higher initial capital investment required for the equipment. This narrative is not about a software update or a clever marketing campaign. It is about the physical layer behind our modern lighting infrastructure. It demonstrates how deep engineering constraints in materials, science, and supply chain manufacturing can dictate the pace of technological adoption far more than consumer demand ever could. The transition from incandescent to LED was not an inevitability, but a hard-won victory for process engineers who solved problems that seemed insurmountable just 30 years ago. Every time you turn on an energy-efficient light today, you are benefiting from a complex interplay of silicon scaling, crystal growth precision, and thermal management innovation that defied the odds to make clean lighting accessible to everyone. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.